the inverse square law, a bit of math. I think I would be doing you a disservice if we took an entire class on studio lighting and didn't explore the inverse square law or take an overview of the math behind it. And here's the thing, when I'm shooting, I promise you I'm not focusing on the math. I'm not calculating the numbers, I'm not doing the squares, but I know how it works and how it's built into the way I think when I shoot. So I'd like to take a moment to introduce you to this law, show you the math at its simplest version, simplest form, and then what it means to you. When most photographers even hear the words inverse square law, their eyes haze over, they start to tune out. But the thing is, light is a science and it's math, but most of us creatives in school, man, we hated those subjects. So right now, I'd like to take a look at the basics of this math without us having to do a lot of calculations. And in a future video, I'm going to explain practical approach of the inverse square law, really how it plays out when you're shooting, what it means to you. So here we go. The fundamentals of the inverse square law. Here is the law simply stated. When you double the distance from the light, you quarter the power. Or if you really want to know the equation behind it, the intensity of the light equals 1 over the distance squared. I never do this math when I shoot, but I understand how it affects the way light behaves and how this affects the way I shoot. The first thing that you should know what this means to you is basically light falls off a lot faster than you think it does. Let's say you move the light from 1 foot away from the subject to 2 feet from the subject. You would half the light, right? No, it's not that. It actually, when you double the distance, you quarter the power. So this means when you go from that 1 foot to 2 feet, you're actually losing 75% of the light, not 50. It falls off faster than you think. And I think it's best understood when it's illustrated, because then you can take a look at why you care. So let's pop over to the studio and take a look at this in action. Okay guys, so we're kind of back in high school, back in math, studying equations, but don't worry, I'm not going to make it that complicated. What I'm going to do is I'm going to explain to you the practicality of the inverse square law, but using the equation. So you'll never need to remember this again. You're never going to have to do this, but instead, I'm going to use this math and illustrate it with the light on the wall behind me. Now, because of that, I actually have to turn off the light on me so there's no ambient light, so you can really see the gradient of light on the wall. That's what you're going to be paying attention to. So let's turn off that light. Okay, so let's put this equation up here front and center. We're going to take a look at it later. So what we've done is we've measured in 1 foot increments from the light. So the light is 0, 1, all the way out to 10 feet. And you can actually see with your naked eye the gradient on the wall. So there's 2 things that I want you to notice. First of all, the light is much more intense, it's much brighter, close to the light. And then further away from the light, it's much dimmer. So the light falls off, it gets darker. But the second thing I want you to notice is the speed at which it falls off. What happens is the light's very bright here, and then it quickly gets darker. But that fall off starts to level out the further you are away from the light. All right, so now it's time for the math of it all. And I actually, I'm going to write the math out on these little pieces of paper, and I'm going to indicate how far they are from the light. So these indicate the number of feet. All right, so take a look at our equation there. What it says is it should be 1 over the distance squared. So what I need to do is I need to square all of these numbers, the distance, 2 feet, 3 feet, 4 feet, and put it over 1. All right, so for example, 1 squared is 1, so it's 1 over 1. Easy enough. 2 squared is 4, so this would be 1 over 4. Right there, that's our inverse square law. We already said it. We doubled the distance, right, from 1 foot to 2 foot, and we went from full power, 1 over 1, to a quarter power. So we've actually already proven our point, but let's take a look at this and what it means for you in practicality. So 1 squared, 2 squared, 3 squared would be 1 over 9. 4 squared would be 1 over 16. 1 over 25. 1 over 36. I'm testing out my high school math here. 1 over 49. 1 over 64. Oh man, math. 1/81, and 1/100. Okay, so this very first fraction tells us a lot. You double the distance, you quarter the power. And every time the distance is doubled, the power quarters. But what I want to do is I'm actually going to convert these to the percentages, because you'll see that what happens is the percentage of light that's lost in the beginning closest to the light, it falls off drastically. But then it levels out the further you are from that light. So let's put the percentages up there. So this is 100%. And then we're at 25%. So again, right away in that first doubling, we've lost 75% of the light instantly. Light falls off very quickly, a lot more quickly than you usually think. All right, so 1/9, 11%, 6%, 4%, 2.8%, 2%, 1.5%, 1.2%, and 1%. Okay, so I've written out all the percentages here. So what you see is you go from 100% to 25% instantly. And then it keeps dropping off, but then eventually that fall off starts slowing down. 4, 2.8, 2. So at this end of the spectrum, far from the light, 1, 1.2, 1.5, there's basically no difference in the light. That fall off has leveled out. The intensity of this distance of this end of the spectrum, it's all pretty much the same. Here's one way to think about it for what it means to you practically. Let's say that you have somebody, you're photographing a couple people. One person is standing 1 foot away from the light, and the next person is standing 3 feet away from the light. If you look at this, the power on them, the intensity is going to be drastically different. Got 100% here and only 11% here. So those two people are going to be lit completely differently. But you take those same two people, bring them down here, same exact distance apart, the difference is 1.5% and 1%. They're basically lit with the same intensity because the light and the fall off has evened out the further away from the light you get. Let's take a look at what this practically means to your photography. Say you want to have a subject that is lit very differently from their background. Basically, you want the background to be darker. All right, well, let's say that I put the subject 1 foot away from the light, and that background is 3 feet away. If I put them 1 foot from the light at 100%, the background 3 feet behind them, it's only 6% of that light that was hitting the subject is hitting the background. So it is going to be much, much, much darker than your subject. But if I do the exact same thing, right? Subject, and then 3 feet behind them is the background. I take this all the way over here. I put my subject here, and then the background 3 feet behind them. If you look, the difference is only from 2% to 1%. So the light is only 1% different. So the background and the subject will be very similarly lit when they're further from the light source. Whereas if you bring your subject in very close to that light source, the light falls off quickly, the background will be darker. This exact same concept applies to lighting groups. I use this all the time for this practical purpose. Let's say that you're lighting 2 people, just 2 people, and one person is 1 foot away from the light, and the other person is 3 feet from the light. They're going to be lit with drastically different intensities. The first person gets 100%, and that second person only gets 11% of that same illumination. They are much, much darker. Well, that's not what I want in a group or a couple shot. So what would I do? I need to move the distance away from the light to where things even out a little bit. So now, if they're the same distance from 2.8 to 1.5, like they're much more similarly lit. The further away I get, the more evenly lit a group will be. All right, so let's put this all together. Closer to the light, light falls off faster. Close to the light, you'll have more intensity of the light. Further from the light, less intensity. But the further from the light you are, that fall off is evened out. So things will be more evenly lit. The inverse square law gives you a lot of control over light when you really understand how it works. In fact, it allows you to control your entire scene, even with just a single light. So remember, when you double the distance, you quarter the power. Or we saw that formula up there. And what it really means to you is that light falls off very quickly. The inverse square law, practical use. As I've said several times before, I never actually do the math of the inverse square law. I'm focusing on the practicality. So if you're not comfortable with the math, feel free to throw it out the window, and let's just focus on what you really need to know when you're working in the studio. We're going to take a moment to take a look at the practical uses you have to understand.